Hi everybody, this video is on section 8.3 and it's going to be on applications to physics and engineering. Now, this section is actually very long because we're going to learn two applications. And so actually what I've done is I've split this up into two videos. So our first application 1, is going to be called hydrostatic pressure and force. Okay, the next video is going to be on moments and center of mass, but both of these applications are going to need to be known for this section. Okay? All right, so what is the idea behind hydrostatic pressure and force? We have a lot of information to write down. So when an object is submerged, the water above you causes pressure. This is called hydrostatic pressure. The deeper you go implies more pressure. So it is definitely dependent on depth. So let's get into a more concrete situation here. Suppose a plate with area A is submerged underwater at a depth, or let me just say at a constant depth of D. Okay, so what does this look like? Let me draw a picture of this. So we've got our water up top. I'm going to use blue for this. So there's our water, and we've got our plate, which is sitting on the ground. It doesn't necessarily have to be rectangular, but it could have any shape. I'm going to go ahead and draw that here. Okay, so this is our shape. It's got area A. And our depth this depth is D. So what we're going to attempt to do is figure out how much force is on top of this thing due to the water. Okay, so let's start by talking about the volume of the water that sits above the plate. You notice that the water that sits above the plate forms a box, doesn't it? Okay, it forms some sort of a box, and I'm actually going to, this should have a dotted line. This one should be solid here. Okay, so because we form what's called a prism, so this is called a prism, or sometimes, this is actually called a cylinder, not a prism. A cylinder. It is actually a rectangular prism, what I drew, but more specifically, it's called a cylinder because it has a repeated shape over and over and over, right? So, what we want to talk about is how much water is above this plate. So notice the volume is actually equal to the area times the depth, okay? And if we had the length and width of the plate at the bottom, we would say that just length times width times height is going to give us the volume. So let's write this down on the next page. The volume of the water above the plate is A times D. Now, suppose the density of the water is rho. Remember, density is actually mass per unit volume. Mass per unit volume. In other words, the density always tells you how much mass is on something given, like per cubic meter or per cubic foot, right? It's always per unit volume. So now that we know the volume is A times D, we can now talk about what the mass of the water. So this implies that the mass of the water above the plate is the density times the volume. So it's density times volume, and so it's just going to equal density times A times D. So we're almost there. We've talked about the mass of the water, but now we want to talk about the weight of the water. In other words, how hard is the water pressing on the plate? So finally, the weight. And what does weight mean? Weight is called force due to gravity. Or that's how you define it. Force due to gravity. Okay? Of the water above the plate is, remember, you always want to write the mass times, and this is something that you should know from physics, but if you haven't taken physics before, that's okay. When you're looking for the weight of something, you always take its mass and multiply it by the gravitational constant. Well, we have the mass. The mass is equal to this thing from before, and so what we're going to do is take that guy and multiply it by g. So this is going to equal rho g a d. Rho g a d. So this is called hydrostatic force. So let's write this on the next line. The force due to hydrostatic pressure of on an object is called hydrostatic force, and is rho g a d. Okay, now this guy rho g, we actually have a name for the product of those two things. So we call delta is a symbol that we use to signify rho times g. So if we call this guy the weight density, then the force is equal to delta times A times D. What does delta equal? Well, it depends on whether we're in the metric system or whether we're in the British system, right? So in the metric system, delta is equal to 9,800. It's called newtons per cubic meter. Okay, it's basically weight per unit volume. So this is for water, okay? And then for the UK system, delta is equal to 62.5 pounds per cubic foot. And again, this is for water. You do not need to memorize these. These values will be given to you on an exam, okay? So, hydrostatic pressure acts in every direction. Now, what this means is that it doesn't just press down, it actually presses in all directions. So if you were to submerge yourself underwater, the hydrostatic pressure is the same as long as your depth is the same. So as an example, if you were to go underwater and let's say that the water is up here, then actually you can think of there being the same amount of pressure all around your head at a particular height. So if you, for example, look at your eyes, right where your eyes are, you feel a pressure, and that pressure is actually on you no matter which part of your head you're talking about. So it kind of forms a circle around your head, if you can picture that. There is going to be a higher amount of force on your feet than there are on your head just because your feet are deeper underwater. Okay? Now, what are we going to do next? So, we will now focus on the scenario of finding the hydrostatic force on a flat surface perpendicular to the surface of the water. Okay, so this is different than the picture that we drew before, right? The picture that we drew before, let me go back to it really quick. the picture that we drew before, our surface that we were talking about at the bottom is actually parallel to the top of the water. But now what we're talking about is a surface that is perpendicular to the top of the water. Okay? This is definitely going to lead to a more complicated situation, and so for this, we are going to use integrals to do. Okay, so let's write this down. This requires the use of an integral. Okay, so that's why it's in this chapter, because again, this is an application of integration. Okay, so what we're going to do is we're going to write out the steps for doing this, okay? So steps for, let me call it steps for setting up an integral for hydrostatic force. So, step 1. Sketch the situation and create a coordinate system. I can't tell you how many people skip this first step. They don't create a coordinate system and then they start writing stuff down that doesn't even agree with itself. So you need to create a coordinate system. Now, a coordinate system requires you to set y equals 0. So set y equals 0. I'll say usually at the surface of the water. And what you're also going to do is you're going to set the positive direction. So you don't just decide where 0 is, you decide which way you have to move for it to be positive. So set the positive direction of y, and I'm going to say usually it's downward. I'm saying usually because that's what I do, but you don't have to do that yourself, okay? It just depends on the problem. And it depends also on how you get comfortable solving these problems. Okay, so once you set up your coordinate system, you're ready for step 2. Step 2. Chop up the shape into horizontal rectangles with equal width delta y. Okay. Now, something that you should note is the distance from y equals 0 to a general rectangle is y. Okay, so we're always going to illustrate our general rectangle when we do the problem, and the distance will always be y from your y equals 0. Okay, so that is step 2. Step 3. Your force, remember your hydrostatic force, is always equal to, we wrote this down earlier, it's going to be delta times the area times the depth. But remember, area is equal to length times width, and so you can write it this way. you can write it like this. The integral of your delta times length, and I'm going to write length of y, and I'm going to write depth of y, and then I'm going to write the width of y over here. So you've actually got length times depth times width, right? Length times width gives you your area, but I split them apart. And there's an important reason for the order that I wrote this, okay? So this is the hardest part of the whole problem. What you want to do now is you want to find the length of y and the depth of y using geometry. Now, why did I write of y on these? I wrote of y because these are functions. They depend on y. So what are some tips here? Some tips for this part is the width of y is always equal to dy in your integral. And one more tip, if y equals 0 at the surface of water, as I recommended, and down is positive, then your depth is just always equal to y itself. In other words, the only hard part of these problems, I'll put a box around it, the only challenging part will be this, finding the length as a function of y. Okay, everything else should be pretty straightforward, given that you did everything that I said to do in these steps. But the length can be tricky. You definitely need to use geometry and see if you can spot a relationship. Okay, once you have done all this, you solve your integral, right? So step 4, integrate. And don't forget that delta is equal to 9,800 newtons per cubic meter, or 62.5 pounds per cubic foot. And I want to also give you another pointer. The answer will be in newtons or pounds, depending on which system you're using in the problem, okay? It's in newtons if you're using the metric system, or it's in pounds if you're using the UK system. Okay, guys, I'm going to go ahead and do some examples. All of these examples require a diagram, and so I'm going to be drawing lots of diagrams for these examples. Okay, so number 1. Suppose a crate is submerged underwater. See the figure. Find the hydrostatic force on the side of the crate shown in the figure. So I'm going to draw this picture on the next page. We've got our water surface, which I'm going to draw here. There's our water surface. And our crate is actually going to be looks like that. And these are the dimensions given by the problem. So this is going to be 2 meters. And this is going to be 7 meters. And this is 6 meters. And I know that I didn't quite draw the picture to scale, but that's okay, right? We're going to go just with the facts as given. So we're trying to find the hydrostatic pressure here. So I'm going to follow the steps as given before. So the first thing that I want to do is, after drawing my figure like I just did, is create a coordinate system. So a coordinate system involves you picking where your y = 0 is, and also picking which way is positive. So I'm going to pick y = 0 at the top of the water, and I'm also going to say that down is positive. Down is positive. Okay. And if you recognize what I said earlier, what I said is that when you create your coordinate system in this way, this means that when you chop this thing up into rectangles, which I'm going to do now, I just drew an arbitrary rectangle whose width is delta y. Then the distance from here to here, let me try that again. The distance from here to here is y. Okay? So, remember, what I said is we need to figure out what the length and the depth are. So the depth of y is literally just y, okay? Because that rectangle has depth y, and you always know that that's true if you let y = 0 and down be, if you let y = 0 where the water is, and you let down be positive. Now what about the length? Now, usually the length is complicated to figure out. However, in this problem, you actually know what the length is. It's just 6, and it's actually a constant, right? It doesn't matter how deep we go. The length is always 6. So let's write that down. And we know that the width is dy. So when you do your integral, it looks like this. The force is going to equal what? So, okay, whenever you set up your integral, there is one thing I should talk about that I haven't talked about yet, which is how you set the bounds of the integral. So this is where the shape begins and ends, so we need to figure out what y equals at these values. So since y = 0 at the top and down is positive, this would be y = 2. Because again, we went down 2 meters from the water to reach the shape. And that means if we go down 7 more, which is what that 7 meters on the left says, that this is going to be y = 9, right? So we are going from 2 to 9, and we're going to do length times depth times width. And so it's just going to be 6y dy. Okay? Now, there is one thing I should put as well. We also have a delta. What is delta? Because this is we're in the metric system here, right? We see meters and stuff. We know that delta is equal to 9,800 newtons per cubic meter, but I don't need to worry about that delta until we reach the end of the problem, okay? So what does this equal? I mean, for now, delta is just a constant, so just let it remain as a constant. So if you take the antiderivative of this, the antiderivative of y is 1/2 y squared. So if I do the 1/2, I'm actually going to get 3 delta and then y squared, and I'm going from 2 to 9. What is this going to equal? I get 3 delta times 81 minus 4, which is 77. Okay. So I get 77 times 3. 77 times 3 is, I think, 291. Let me just check on my calculator. Sorry, 231, I mean. So 77 times 3. So we get 231 delta, or remember, 9,800 is my delta. So if you multiply 231 by 9,800, you end up with 2,263,800 newtons. You don't need to worry about the newtons per cubic meter, because when you multiply that by the 231, you end up with newtons, because the 231 is a volume. It's actually in cubic meters here. So this is the total amount of hydrostatic force that is on this rectangular shape that's submerged in the water. Okay, let's do another example that is definitely more tricky. Okay, so let's look at number 2. Find the hydrostatic force on the figure below. So again, we've got our water, and I'm going to draw my shape here. I actually have I'm going to draw it this way here. So we've got this shape. These two sides are the same. And I need to put some dimensions in here. So from here to here is 10 meters. From here to here is 30 meters. And from here to here is 40 meters. And then from here to here is 60 meters. So this is my shape. Okay, so again, start off by making your coordinate system. So I'm going to call y equals 0 at the top, and down is positive. And then I'm going to put my rectangle in here. So let's put my rectangle right. Oh, you know what? I'm going to use, let me actually make this line a little higher up here. I'm going to make my rectangle into a straight line here, just so that we don't. Let me back up here. Let me try this again. this is our rectangle, okay? This has width delta y. So what we're trying to do is we're trying to figure out the length of this rectangle, and that's going to be a lot more tricky than it was in the last example. But let's write in what we do know. We know that when we have y equals 0 at the top and down being positive, we always know that this guy right here is y. Okay, so that's what we know. So let's go ahead and write that down. We know that the depth as a function of y is just y. And we also know that the width as a function of y is, of course, it's delta y, but we're going to write dy because that's what's going to go in our integral. Now comes the tricky part. We need to figure out what this length is. So here is the trick for this problem. The trick is to, so what we're trying to do is figure out how this length here relates to the depth y. In fact, we need to find it as a function. So I'm going to break this up like this using similar triangles. Okay. Now, if I make that similar triangles, remember we had 40 meters is that top distance. And so what we know is that this is 40. We know that this is 40. And then we have some unknown amount here and some unknown amount here, right? So I'm going to call those A. They must be the same because this is an isosceles trapezoid, right? So we know that those two are the same. So we need to figure out what A is. And so what we're going to do is we're going to look at similar triangles here. Similar triangles. And here's going to be our two triangles. So here's our two triangles, and we're going to fill in the dimensions here. So this is A, and what, let me keep going here. This distance is 30, right? And then we know at the very bottom, this is 20, and this is, not 20, sorry, 10. This is 10, this is 40, this is 10, right? That's the only way that we could get 60 if those two are the same. So this is 10. And so what is this part here? So what is this part going to be? Well, I want you to think about it. The entire distance is y that goes from the top of the shape to the rectangle. Sorry, from the water to the rectangle. And then from that top of the shape, that's just going to be y minus 10. Right? Because y is the entire distance. So we are doing this guy minus this guy, right? If you do y minus 10, you would get just that distance that we showed right there. So this is going to be y minus 10. So finally, we can do a similar triangle argument to try to find A, right? So it's going to look like this. We could say A is to 10 as y minus 10 is to 30. Or A, if I multiply both sides by 10, I get 1/3 times y minus 10, which is 1/3 y minus 10/3. So what is the length as a function of y? Remember, A isn't the whole way across. It's just this piece. And so we need to add 2 of those because there's 1 on each side and then add it to 40, right? So it's 40 plus 2 of those. So I'm going to multiply what I just wrote down by 2. 2/3 y minus 20/3. But what's 40 minus 20/3? That's 100 over 3. And so we end up with 2y over 3 minus 100 over 3. Sorry, I just realized that I made a mistake here. This should be a plus, right? Okay, so we have everything that we need to do this integral, right? We've got these two, and we've also got our length. And don't forget, we have to multiply it all together. There is one last thing we should write down on this page before we go to the next page. We need to write down where our starting and ending y values are for the shape. So this is y equals 10. And this guy down here, because we've gone down 10 and then 30 more, this is going to be y equals 40. Okay, so we're ready to write down our integral. So we are integrating from 10 to 40. To 40. We're going to do our delta, and then we're going to do our depth, and then we're going to do our 2/3 y plus 100/3. And then I have my dy. Okay? What I'm going to do now is I'm going to pull out the 2/3 and the delta since it's just the constant. So if I pull out a 2/3 delta, what I'm left integrating here is from 10 to 40 of y squared plus 50y dy. So what do we get here? So this is going to be 1/3 y cubed and then plus 25y squared. And we're going from 10 to 40, right? So what do we get if we multiply 40 by itself 3 times? So 40 times 40 times 40, 64,000 over 3. So here's what we end up with. 64,000 over 3 plus, and then here, if we square 40 and then multiply it by 25, we get 40,000. And then I'm going to do minus, if I plug in 10, I get 1,000 over 3. And then I'm going to do minus, plugging in 10 into the second term, we end up with 2,500. Okay, so what do we get if we put all of this in our calculator? So I'm going to use that now. I have 64,000 over 3 plus 40,000 minus 1,000 over 3 minus 2,500. You end up with 2 delta over 3 times 58,500. So what does that become? I get 39,000 delta. Or, remembering that delta is 9,800, I end up with 3,822, 1, 2, 3, 4, 5 zeros. So that is going to be 382,200,000 newtons. This is going to be the force on that isosceles trapezoid that we saw in our beginning. Okay, guys, so the hardest part for this example that we just did was definitely the setup here. Trying to figure out what the length of this rectangle is, right? This entire length right here. Trying to figure out what it is as a function of y. So that's what we were able to do using our similar triangle argument. Okay, So I'm going to work on number 3 now. This will be our last example, and I'm going to illustrate what to do when you have a circular shape, okay? All right. So number 3. Find the hydrostatic force on one end of a cylindrical drum shown in the figure. So I want all the room I can get here, so I'm going to do this on the next page. So let's start by drawing the water here. And this is going to be my cylindrical drum. Our drum looks like this. Please pretend this is a circle. Oh, it looks like, actually looks like, I can do it better like that. So, let me draw some dimensions here because we need these dimensions for our problem. We're going to suppose that it is 10 feet deep. And we're also going to suppose that the radius is 3 feet. So let's do it this way. We're going to say the radius is 3 feet. Okay, now we could let y equal 0 at the top of the water here. However, there's actually a better way to do it when you're dealing with circular stuff. When you're dealing with circular stuff, I actually recommend that we're going to let y equal 0 in the inside, right on the center. So I'm going to say y is equal to 0 here. Let me draw that a little bit. Not as dark here. There we go. Y equals 0. It doesn't really matter which way is positive, so I'm going to say that down is positive, but it's actually not going to matter when you do this problem, okay? And we're going to draw our rectangle. So let's go ahead and chop this thing up. You can't put the rectangle in the middle. So there's our rectangle. And this guy has width delta y. Remember, normally you know that, normally we know that the depth is y, right? But you don't have that this time because of where the y equals 0 is, okay? So let me go ahead. I'm actually going to go to the next page here. It helps if we are looking at a bigger circle here. So what I'm going to do in the next page is draw this circle again, except draw it a little bit bigger, and I'm going to actually draw it not to scale. That way we can do a little bit of analyzing on it, okay? So here's our circle. And we've got our water is here. And I'm going to start drawing some stuff that we know. I'm going to draw my rectangle. There's my delta y. And I have that y equals 0 is right here. This is y equals 0. So I actually said before, when I first set up this problem, I said, or not this problem, but when I set up my steps earlier, and let me go back to my diagram, or my steps here. What I said is this: the distance from y equals 0 to a general rectangle is always y. And we're used to that being the top, but in this case it's the center of the circle, and so I know that this distance right here is y. Okay? All right. So let's start with the depth, because the depth is not so obvious now. We need to figure out what this distance is. So remember, this is 10 feet. And we also know that this has to be 3 feet, doesn't it? The reason we know that is because we know the radius of the drum is 3 feet, and we also know that it's 10 feet deep, right? So that's where we got those two numbers from. So then what would that distance be? We know that the total distance down is 13, but then we have to take away the y. Okay, so we know it's going to be 13 minus y. That's going to be this guy right here, 13 minus y. Okay. All right, so this is the depth. So we're ready to write that down. We know that the depth is 13 minus y. Now what? We need to talk about the length, right? Or how about I write down the width, because we know already that that's dy, because that's always dy. So we need to figure out how long that rectangle is. And so the trick in using geometry here, in this case, the key is going to be the Pythagorean theorem, because we know what this distance is, don't we? This distance right here is 3. And so if that distance is 3, then that means we know by the Pythagorean theorem that from here to here, half of that, or half of the length, is equal to the square root of 9 minus y squared. So if that distance is the square root of 9 minus y squared, we know the length is double that, right? And so we're ready to write down the length. The length is 2 times the square root of 9 minus y squared. What about this and this? By the way, I should write down, you know what? I'm just going to go with, the way I treated y here was like it was a positive number, so I'm actually going to say that up is positive. Okay, up is positive. So that means if up is positive and y equals 0 is in the center of the circle, then that means that this guy would be y equals 3, and this guy would be y equals negative 3. Okay, right? We've got this guy and we've got this guy, right? So we're ready to write down our integral. We know that the hydrostatic force then must be the integral from negative 3 to 3. And we know we have a delta. And so I'm going to first write in, so I guess I'll write 13 minus y times 2 root 9 minus y squared. I'll write it that way. 13 minus y times 2 root 9 minus y squared dy. We're going to get to do a lot of simplification in a moment, okay? But this is what we have. What I'm going to do is I'm going to pull out the 2 delta. So if I pull out the 2 delta, I'm then going to split it up into 2 integrals. I have negative 3 to 3 of 13 root 9 minus y squared dy. And then minus the integral from negative 3 to 3 of y, the square root of 9 minus y squared dy. Okay. Now, how would I solve this? I'm actually going to use some tricks to solve these integrals because these integrals actually have some really nice stuff that we can do if you remember our tricks from Calculus 1. So I want you to look at this first integral here. What is negative 3 to 3? If I pull the 13 out and I have just 9 minus y squared dy. I can do this integral using a trig substitution if I really wanted to go that far, but I actually don't even need to do that. And the reason for that is because this is a half circle, isn't it? What would this look like? I'm hoping you guys remember that, if you have a function, square root of 9 minus x squared, you're actually talking about an upper half circle, and we're going from negative 3 to 3, and so really, this is just the area of a half circle. And we know what that is. That's pi squared over 2, isn't it? So it's going to be 13 times... pi r squared over 2, right? Pi times 3 squared divided by 2, which is equal to, what is 9 times 13? 117. So we get 117 pi over 2. That's what I get for my first integral. What about my second integral? Now this is not a hard integral to do. You could just let u equal what's under the radical. However, there is a trick we can do, okay? Because we're going from negative 3 to 3, and I want you to notice something, the inside function is actually an odd function. This is an odd function because if you plug in negative y, you get a negative of the entire thing. And so we know by symmetry, if we're going from negative 3 to 3 of an odd function, we get 0. So, putting these two things together, this means that we get 2 delta times 117 pi over 2. Or, cross those off, we actually get 117 delta pi. But remember, in this case, delta is 62.5 because we're talking about, everything was in feet, wasn't it? So we're talking about UK units. So if we do 62.5 and then we have a pi here, I do 117 times 62.5 and I'm left with 7312.5 pi, and that's in pounds. Okay, you got to have pounds here because remember, those are the units that you deal with. Those are the units of weight that you deal with when you're talking about feet and stuff like that. Okay. Big change here, right? The change in this problem was that we called y equals 0 the center of the circle. Now, you could have done this problem with calling y equals 0 the top of the circle. Then your depth would have been y, except your length would have been a lot more complicated. Okay, so I chose to do it this way because it works out as cleanly as possible when you're actually setting it up. So my rule of thumb is anything that is not a circle, call y equals 0 the top of the water, but then anything else, you're going to, or not anything else, but when you have a circle, call y equals 0 the center line that goes through the circle. Okay, guys, I hope this video was helpful. That's it for this lesson. Thank you so much for watching.